I'm a rising second year at the University of Colorado Boulder. I am talking in place of Alex, and I'm going to be talking about the changes from INFUSE. Okay, so first of all, what is INFUSE and SUMO? INFUSE stands for the Integral Field Ultraviolet Spectroscopic Experiment. The current new targets for INFUSE is NGC 2366 and Markarian 71. They're a pair of dwarf galaxies. I also included an image of the simulated spectra that we're expecting to see in this observation, where I highlighted that our main spectral targets is going to be oxygen 6 and carbon 4. I also wanted to mention, just like Emily had already done so, the technology in INFUSE is going to be used as a tech demonstration for Habitable Worlds Observatory. And then SUMO stands for Spectroscopic Ultraviolet Multi-Object Observatory. There's a little image of it, and just briefly, essentially SUMO is going to be able to either image what we're looking at or take spectroscopic information. Before I get into what INFUSE is all about, I just wanted to give a quick shout out of all the people and the community at LASP. I wanted to start off with the PIs, Brian and Dimitri. And then we have the senior grad student. He's the one that couldn't show up today, but he's showing me all of the ropes. There's me holding the new grading array. And then we have master's student Will, who's responsible for all the electronics in SUMO, and our undergrad Leo, who is essentially doing whatever we throw at him. And then we also had people graduate from our project, including Emily and Grace. So just to put into perspective of what INFUSE is capable of, let's just for a brief moment say we're all scientists, and we want to look at the antenna galaxies. I chose this pair of galaxies because there is a lot of science interest in here. Where the darker regions, you can expect some star formation. I also chose it because of the spatial resolution, so it's a lot closer, and we can take advantage by really trying to understand the morphology there. So say we want to use the Hubble telescope, there's a variety of instruments that you can choose from, but if you want to get an image that, much like what you see there, you would use the wide field camera. But if you want to be more specific and get spectroscopic information or composition of these galaxies, you'd want to use COS, the Cosmic Origin Spectrograph, which looks into the ultraviolet. And so let's say there's a lot of interesting areas. Say I wanted to look at the composition of one of the galaxies, we can point it in towards this area, or how do these change if you're looking in the merging area, or even how this galaxy interacts with the rest of the universe, the outflows. As you can imagine, getting the whole picture starts to become more difficult as you require more pointings. But the idea with INFUSE is that it can observe all of it at the similar resolution as COS does. Another way to think about it, if we want to think in terms of math, which I know you guys are all very excited about, how much time and how much orbits would this look like for COS? So this is kind of like the direct comparison of them. So let's say we want to look again at the antenna galaxies with INFUSE for 300 seconds. So we can expect the same resolution. INFUSE field of view is about 3,600 times larger than that of COS. We have to also think about aperture and throughput, because COS's aperture is about 2.5 arc seconds, where INFUSE's is 2.5 arc minutes. But if we do some calculations, we would get that it would take about 54,000 seconds to observe the same area that INFUSE does. That's about 15 hours. In terms of orbits, a Hubble orbit is around 95, which ranges between 25 to 44 because things get in the way. But if we give it the benefit of the doubt, let's say that it takes the most 44 minutes, 40 seconds. We can take that ratio that we did earlier and get a total of 20.45 orbits. I would not want to propose this, but essentially the idea for INFUSE is that we want to enable scientists to get the whole picture without the sacrifice of resolution. Okay, so a little bit about INFUSE now. There's not a lot of changes that have happened since the first flight in terms of what's on there. It's still going to have the same electronics and star tracker and essentially the same kind of design. So if you can imagine, here's the shutter door closing, just picture it in reverse in space, it'll open up, and light will come in through the right. This is a Cassegrain telescope, so it'll bounce off of the primary mirror, which is parabolic, and then onto the hyperbolic secondary mirror. That'll then converge all of the light through the baffle tube past the primary mirror. And this is where all of the more juicy stuff happens. This first thing it'll come into contact with is the image slicer, which is the thing that really enables the IFU technology, then bounce onto the grading array, and then onto the detector. I'd also like to mention that we've had a few mechanical improvements since the first flight, especially with the C channels, where we noticed there was a bit of a weak point. We kind of buffed them out there. And the C channels are essentially responsible for holding the electronics deck to the bulkhead. In addition, there was also a leak that was found in the first iteration of the rocket, but we found the source of that leak and fixed it. And so now it's able to perform by around a factor of 100 times. And then in addition to that, in the event that we have another leak, we're also testing getter pumps for specifically a sounding rocket application in case that ever happens again. Okay. So now to get into each of the little pieces of technology, I'm going to start with the image slicer. This is, like I said, what really enables our IFU technology. And as the name implies, it's responsible for splitting the light into different sections. In the second version of the flight, instead of lithium fluoride, we are now using xenon-enhanced lithium fluoride, which has already shown a lot of promise in that it's very stable, it's a lot more smoother, and I believe, yeah, it's a lot smoother. And it has better reflectivity in the lower wavelengths, especially in oxygen 6, which is one of our target wavelengths. Next, I wanted to talk about the far ultraviolet grading array. There's the new one there. It's 25 of the lithium fluoride, 25 of the gratings are lithium fluoride, and one of them is going to be that xenon-enhanced lithium fluoride. It now has a gold coating on there to reduce the scatter. And also in the middle picture, you can see there's a unique spectrograph design. This normally was symmetrical, but now has a lot of cross. And this is to reduce scatter by adding room for a baffle. Additionally, our undergrad is working on a system, this like weird little box thing there. This is going to be there to help us align the grading a lot quicker by letting us access the grading array at air pressure under a strong nitrogen purge. And then I wanted also to talk about the microchannel plate. This is the large format cross strip MCP. It's 94 by 94 millimeters. And I'd just like to note that this is the largest one ever made. And then also to compare what our data would look like in a lab environment versus what we saw on the first flight. You can see that the lines are a lot stronger because we're using a lamp spectra, but they're going to be a lot more dimmer. On the flight data image, you can see there's a bunch of these much more darker lines. These are the geocoronal Lyman alpha lines. But above and below is where our area of interest is, where those carbon 4 and oxygen 6 lines are going to occur. I'd really like to point out that in the middle, there's that image slicer shadow, and above below, there's a lot of scattering happening. And this is what we're really looking to reduce in the next version of the flight. Okay. Just to summarize what technology specifically were demonstrated for the Habitable Worlds Observatory, we're testing large format MCPs, we're testing integral field unit technology, which is scalable to be smaller or larger, and we're testing Z-lift coatings. Okay, and then don't forget about SUMO, the Spectroscopic Ultraviolet Multi-Object Observatory. This is going to be the first application of digital micromirror technology in space. There it is sitting on top of our electronics desk. It's completely isolated, but as you can imagine, light coming through the telescope, it's going to hit that DMD. There's a blown up version of that DMD up in the upper right, showing the LASP logo. These things are in like micrometer scales. And on our DMD that we're going to be flying, it's going to be around 700,000 of them, so they're quite small. But essentially, once it hits the DMD, it allows us to use the dual channel, so it'll either go to the diffraction gratings or the mirror, so we can either image it or get spectroscopic information. And if you want to read more about it, I included the paper by Halferty et al. that really describes and goes more in depth about the technology. Last thing I wanted to say, we were supposed to fly this fall, and we're still on schedule to do so, but currently NASROC is out of flight termination systems. And I also wanted to thank all of the community that I've been interacting with at Boulder. They've been wonderful and have made my first year in grad school a great experience. Thanks.